Morning, everyone. How are we doing? Nephew's birthday. Morning, everyone. Questions while we're waiting? Booker T? Absolutely. Yeah, we're doing more trig integrals today. Let's consider this while we're waiting. If the x wasn't there, honestly, I don't know how people study with music on. Yeah, I'd find it impossible to concentrate, and I can't work with music on. Consider this. Again, the idea is if the x wasn't there, this was Booker T and the MGs, green onion. So if the x wasn't there, this would be easy. How are we going to get rid of the x? By differentiating it. So integration by parts. U is x, dv is the rest. du is easy to see. V, maybe not so easy. So let's take a moment, and how would you integrate sine x cos x dx? You see that the derivative of sine is right here. So a simple u substitution, absolutely. If you see it, 1/2 sine squared, and we're good to go. Absolutely. If you don't see it, do a u substitution here. So again, if you don't see it, a w substitution. And so this becomes w dw, which is 1/2 w squared. So 1/2 sine squared. I mean, we haven't done we've only been looking at sine and cos. We're going to do a lot more today. So this becomes uv, 1/2 x sine squared, minus the integral of v du. Let's take the 1/2 out again, sine squared dx. So you see your second integral doesn't have an x anymore. So it's a lot simpler. And you know how to integrate sine squared. All right, we're going to use the half angle identity. Sine squared is 1/2 times 1 minus cosine 2x. Now you can just integrate term by term. Antiderivative of 1, antiderivative of cosine 2x, 1/2 sine 2x, throw in your arbitrary constant, and there you go. Very nice. Sean, what happened there? Question? What do we do to sine squared? We use the half angle identity. Sine squared x is 1/2 1 minus cos 2x. This is what we use to integrate sine squared, and we have a similar one for cosine squared. Cosine squared is 1/2 1 plus cos 2x. How do we do the antiderivative of cosine 2x? Well, you can make a u substitution. U equals 2x. And then you'll just have cosine of u, whose antiderivative is sine u, and you'll have a 1/2 outside. How do we know, if he's asking, how do we know which values to get to u and dv? Experience is the answer. Lots and lots of exercises. It'll come naturally. In the beginning, you do something, it's not working, you try something else. Here, the idea was, if we can get rid of the x, the integral is easy. Well, let's not say easy. If you can get rid of the x, the integral is doable. How are you going to get rid of the x? By differentiating it. So that's why you let u be x. Let's try a few more integrals involving sine and cos. I don't remember if we did this one last time. It might have been our last question, but I don't think we did it. So let's try it now, if we did not. Very good. Right, I mean, last time we saw if you could isolate one sine and everything in terms of cos, then you can make a u substitution. If you can isolate one cos and everything else in terms of sine, you can make a u substitution. This works very nicely if you've got one odd power of either sine or cos. We don't have that here. Here we have even powers of both. We just saw how to integrate sine squared using the half angle identity. Here, we'll do the half angle for both. Easily seen to be this. The one we can integrate with relative ease, and then you've got cosine squared. which you're going to integrate in the same way we did sine squared. Half angle again. One plus cosine. 1 plus cosine, you know what's happening here. You double the angle, right? Cosine x becomes cosine 2x. Cosine 2x becomes cosine 4x. Thank you. Well, I mean, maybe we can write it here. 1 minus 1/2 is 1/2, so that is 1/2 x. And then you've got 1/2 cosine of 4x, whose antiderivative is 1/8 sine 4x. Throw in your arbitrary constant. There we go. Why did we do half angle for both and not just for sine? If you do for sine, you'll have a cosine 2x and then a cosine squared of x. And we'll see, I mean, it's not nice. It's not nice. You've got cosine 2x and cosine x. It's not the same argument. It's not... We'd like to stay away from that if we can. Let's move on away from sine and cos, but not that far away, right? Because you know all other trig functions are can be rewritten in terms of sine and cos anyways. Why the negative here? Well, I mean, the negative distributes, right? The antiderivative of cos is positive sine. Consider the integral of tangent. Integral of tangent, which we can conveniently rewrite as sine over cos. And then you recognize, right? You recognize the derivative of the denominator as being the numerator, essentially. Right? So if you make a u substitution, right? This becomes negative 1 over UD. If he's asking how we get the 1/2 x, you have a 1 minus 1/2. So that's 1/2 antiderivative 1/2 x. Marie's asking why not make a u substitution with sine x. If you let u be sine x, du is cos x, but you don't have the cosine x there. You have the 1 over cosine x. Not the same thing. So this is the way to go. And of course, antiderivative is easily seen to be ln, negative ln of absolute value of u, or ln of absolute value of cosine x. Some books, including ours, likes to bring the -1 back up using properties of logarithms. And you can rewrite this as log of cos x to the -1. And 1 over cos x is secant. So some books like to give this as log of secant, but I personally prefer this. It's easier to see. You tell me. No. Well, Liam is asking, do we need to give a proportion of the constants, right? I mean, if you're doing integration by parts, maybe you have two different constants. No, just the one is fine. Yeah, I mean, it's not cos inverse, right? It's 1 over. So this is non-notation for the inverse cosine. This is notation for 1 over, because by properties of logarithms, you can bring the -1 up. Right? Thank you, Paul. Everybody remembers that the derivative of tangent is secant squared. So there's nothing to do here. Similarly, the antiderivative of secant tan right? What function has derivative secant tan? You know that to be secant. Thank you, Matt. Right, so we're moving away from products of sine and cos into the other trig functions. We did tangent, we did secant squared, we did secant tan. These are all nice and easy. Let's consider the integral of secant. Do integrals and antiderivatives mean the same thing? I use them interchangeably. Are you referring to these two things here? I mean, look, you know the derivative of tangent is secant squared and so on. You can take these for granted. We're going to do more than that today. Absolutely. The day is still early. Integral of secant. Not so easy. Yeah, so I mean, look, first of all, these, you can take these for granted. These are known antiderivatives. And of course, I'm not going to ask you for these integrals on an exam as a question on their own. I mean, they may come up after doing lots of work and some simplification of this and that, and then you can just say, well, antiderivative of secant squared is tangent, we're done. Integral of secant, this requires a nice trick, and the trick is to multiply by 1. Tempting, let's not do it. Let's not do it because if you do integration by parts, you're going to I mean, if you do the obvious integration by parts by letting u be secant and dv be dx, you're going to introduce an x, which is not going to be a good idea here. You could maybe do something else, though. Let's not investigate that. The typical way to evaluate this is to multiply by 1. Tempting. I mean, you can try writing it as 1 over cos x. It's not going to help you very much. We're going to multiply by 1. So, when you multiply by 1, you don't change anything. Tempting. I'll let you try that, and then maybe do an integration by parts. Not by tangent, but by secant x plus tangent x over itself. I'm multiplying by 1, so I'm not changing anything. It's all good. And what does that do? Well, I mean, let's multiply that through. This is secant squared plus secant 10. And while that seemingly doesn't do very much, we multiply by 1. We just multiplied by 1, namely secant plus 10 over itself. We're multiplying by 1. We're not changing anything. Right. Rachel is asking how you know to multiply by this. Well, I mean, I didn't come up with that. It's the typical way to solve this integral. And what do we notice? If you take a step back, I mean, it's not immediately clear what's happening and why this is a good thing to do. But you'll notice that the derivative of the denominator, what is the derivative of the denominator? Derivative of secant is secant 10. Derivative of tangent is secant squared. The numerator, as the one name suggests, the numerator is the derivative of the denominator. So making a u substitution does the trick. And this is exactly what you have there. So this just becomes 1 over u du, which is ln of absolute value of u, or ln of secant plus 10. Isn't that amazing? How are we doing? Anybody? Questions? All right, a seemingly easy integral, secant. Inconspicuous, really. Boom. I'll let you repeat with the integral of cosecant. You can do cosecant in a very similar way. What pattern are you seeing, Matthew? consider interesting. Very well. And similarly, cotangent and cosecant will have integrals with bonds as well. Let's consider secant cubed. Let's consider secant cubed, which we will conveniently rewrite. Well, as secant times secant squared. Absolutely. And then we're going to do integration by parts. Yeah, I don't have an answer to that, Matthew. Graphically, I don't see why why you might expect a lawn to come in. Could you do U sub for secant? I mean, if you just look at secant on its own, which is really 1 over cosine, right? I mean, you might be tempted to say U is cosine x, but then du is negative sine x dx, and you don't have a sine. So that's why you don't want to go that route. Here, if we're doing integration by parts, du, derivative of secant is secant tan. And antiderivative of secant squared, you know what that is. That is just tangent. Could you do a U sub for secant cubed? What would you suggest? Maybe. You know, there may be more than one way to do these things here. And some people were suggesting multiplying by sine over sine and that kind of thing. I mean, or tangent over tangent. It's possible. I mean, I don't know that it's going to work, but I'll invite you to try it out, see what happens. If we do this, Rudy, you were going to suggest a U sub for secant cubed? Tell me. So integration by parts on this, uv, secant x tan x, minus the integral of vdu, secant x tangent squared. If u is secant, then du is secant x tangent x, but you don't have a tangent anywhere here. And that's the problem. To answer Matthew's question, there may very well be a good reason why lawn shows up. I don't know that a priori you would expect it to. I've never given it any thought, but I mean, maybe there is a reason. Paul doesn't see a u sub in your second one, and you're correct. It's not going to be u sub. Now we're going to start talking about identities involving the other trig functions. Now you know a very important identity, sine squared plus cosine squared equals 1. Let us derive an identity involving tangent using this. If you multiply this whole equation by 1 over cosine squared, if you multiply the whole equation by 1 over cosine squared, equality is maintained. And what do we get? We get sine squared over cosine squared plus cos squared over cos squared, which is 1, equals 1 over cosine squared. Or tangent squared plus 1 equals secant squared. And you can get a similar identity. Instead of multiplying by 1 over cosine squared, if you multiply by 1 over sine squared, you get 1 plus cotangent squared equals cosecant squared. So if you replace tangent squared here, if you replace tangent squared by secant squared minus 1, and expand this out, so this times this is going to be the integral of secant cubed. Let me split it up into two integrals. And then you get minus secant, so minus minus. And this integral is the integral you started out with. So bring it over to the other side. You know the trick we did before. If you bring it over to the other side, you get two of them. So the integral of secant cubed is 1/2 of this stuff. Right? Isn't that amazing? And the integral of secant we just did together a moment ago. So this is secant tan minus ln of secant x plus tan x. Throw in your arbitrary constant, and you're done. If you bring this secant cubed to the other side, you get two of them, and we divide by 2. Yeah, y is a negative. It's not negative. It's not negative. Thank you. Look, we've seen this trick before, right? You have this integral is equal to that minus the integral. So you bring that integral to the other side, you get two of them, and then you divide by 2. Why is there a second integral? Well, I mean, it's the integral of secant cubed minus the integral of secant. I have broken up the integrand into two separate integrals. Convinced? Let's try another one. Correct. It doesn't matter if C is inside or outside. If C was inside, you'd multiply it by 1/2. So you would get 1/2 C. But C is an arbitrary constant. So the 1/2 gets absorbed into it. And it's all good. Secant minus 1. But we have a negative here. So that's why it's positive. Right, we have two negatives. We have a negative outside the integral as well as a negative inside. Consider this. Exactly, right? This is very easy compared to what we've been doing. U equals tangent. A simple U substitution does the trick, because you recognize that the derivative of tangent is right here. And you can generalize, right? If you've got an integral involving secants and tangents, if you can isolate one secant squared and everything else in terms of tangent, you're good to go. Or vice versa, if you can isolate just one tangent or one secant tan and have everything else in terms of secant, a simple U substitution does the trick again. So this easily becomes 1/2 tangent squared. There it is. Certainly you have to be comfortable with the derivatives of the trig functions. Right, and remember what I said when we first started this course, you don't need all the knowledge of Cal 1, but certainly the derivatives. You need to be able to differentiate all trig functions immediately. Well, I mean, it's the integral of U du, which is 1/2 U squared, 1/2 tangent squared. Consider this. What are we going to do? Sophie's asking if it would also work if U is secant. Very nice. Very nice, right? An excellent observation. And why don't we take a moment to discuss that? So let's redo this exact question as Sophie suggests and make a secant substitution instead. If U is secant, what is du? Du is secant x tan x dx. And so this, which breaks up as secant times secant tan, this secant x tan x dx is your du. So this just becomes u du, which is 1/2 secant squared. And now you're thinking to yourself, well, that's not the same answer. That's not the same answer at all. All right, I mean, here we have tangent squared and here we have secant squared. These are not the same. But they are, right? These answers agree because we know that tangent squared plus 1 is secant squared. So this is really secant squared is tangent squared plus 1. So this is 1/2 tangent squared plus 1/2 plus c. And if c is an arbitrary constant, adding any other constant, yeah, I tried to unblock him. It was a mistake. And now, I mean, can Jun Chen still write? Can you try writing? Sorry, I believe I unblocked you. It was my mistake. Yeah, so my point is that c plus 1/2, he should be able to write. I did, it's not working. Seriously. All right. I'm sure it'll be fine next time. Sorry about that. Right, so the point is that the two answers are the same. And we're good, right? The 1/2 gets absorbed into the arbitrary constant. And we were going to talk about secant squared, tangent squared, which is really the same thing, right? It's really the same thing. You can make a u substitution. U equals tangent, because the derivative of tangent is right here. So this just becomes u squared, or 1/3 tangent cubed plus c. I'm not sure why it's not working. All right. Shall we do a few questions from the book? Right, so the point of doing this other of doing this other u substitution was to point out that, sometimes you'll see an answer in the back of the book and it seems completely different. But they could very well be the same thing. All right. There's no need to give a range of the C, and there's no need to rename 1/2 plus C, maybe a C1 or a C star. It doesn't matter. Most people are just going to absorb the 1/2 into the C and say it's plus C anyways. Marie is suggesting to isolate one of the signs, and that's exactly what you want to do. Nicely done. So we have a cosine to the 6. We'll rewrite the sine cubed as sine squared times sine. And now, if you can rewrite this in terms of cosine, then you see what's going to happen, right? A simple u substitution and you're good to go. And that's exactly, this is very easily doable. This is 1 minus cosine squared. And now a simple u substitution does the trick. So this is easily seen to be u to the 6, u squared minus 1, du. Is there some sort of implicit integration that we're going to study? Not so much. You kind of do that a bit in differential equations. And it also comes up in advanced calculus, kind of. Yeah. Yeah, exactly right. The negative was absorbed. It should have been 1 minus u squared, but I changed it to u squared minus 1 because of the negative. Yeah, so 264 or 263, you kind of do it in both places. Of course, it's not referred to as an implicit integration, but that's kind of what's happening. Kind of. Yeah. So integrate, expand and integrate. 1 over 9 cosine to the 9 minus 1 over 7 cosine to the 7. Is everybody able to do this in their head? What if it was cosine instead, or cotangent? Well, yeah, who knows what happens then. Somebody still doesn't see the flip because of this negative here, right? This is negative du. So if I have 1 minus u squared and I have a negative outside, I can multiply the negative in there. So let me not skip any steps here. This is u to the 6. First, this sine y dy is negative u. So negative du. This is u to the 6. And this is 1 minus u squared. So this is u to the 6 minus u to the 8. With a negative, becomes u to the 8 minus u to the 6. Does everybody see it? This is u to the 8 minus u to the 6. Do the multiplication. And then you get a 1 over 9 u to the 9. Minus 1 over 7 u to the 7. And now you're back to there. Yeah, so 263 or 264 if you're doing engineering, but I mean there are math equivalents, right? I think it's I want to say 314, 315, something like that. Questions? You can take them as electives. It's all good. ODEs is a very nice course. Ordinary differential equations. So, you know, I mean, it's as simple as calculus. Are you not allowed to subtract the u's? I mean, they are different powers, right? U to the 8 minus u to the 6, this does not subtract. Yeah, absolutely right, Paul. Thank you. We're going to you know how to integrate cosine squared, the half angle identity. So this is the integral from 0 to pi over 4, 1/2, 1 minus cosine 4 theta. Very simple exercise. I mean, it is number 8. Finish it up. Let's take the 1/2 outside. This is antiderivative theta minus 1 over 4 sine 4 theta between 0 and pi over 4. Sine of 0 is 0. Sine of pi is 0. So this doesn't bring anything to the answer. And we just get pi over 8. You may have noticed yes, this encompasses the whole thing. Absolutely. Yeah. right? I mean, you have your antiderivative here. So you plug in the top limit and you subtract plugging in the bottom. You have to do, so somebody's asking if we only practice the exercises from class. That's not enough. That's not enough. Because first of all, we already did them. So, I mean, it's nice that you review them to get you started, but you really have to do lots of questions on your own from the book. This is how you master the material. This is how you're going to learn the material and do very well in the course. And speaking of exercises we're looking at, you may have noticed that we did stuff with sine and cos. We did stuff with tangent and secant. We did not do any with cosecant and cotangent. The reason is that stuff with cosecant, cotangent is the same as stuff with tangent and secant. So I'll let you do those, but they're tackled in the same way. If you give me an integral involving cosecant and cotangent, you can rewrite that same integral using secant and tangent instead of cosecant and cotangent respectively, and the integral will be done in exactly the same way. What is suggested here? Change secant squared to tangent squared plus 1. So you're suggesting to rewrite this. The secant squared secant. And then this secant squared is tangent squared plus 1. Nothing wrong with that. Absolutely. Yeah, I mean, everything's fair game in office hours. Please feel free to ask anything, anything you want. All right, an excellent start. An excellent start. But I mean, you understand that now you cannot say, I'm going to let u be tangent because I've isolated a secant. It doesn't work, right? Because the derivative of tangent is secant squared. If you had isolated a secant squared, that would have been good. But this is not possible here. Somebody's suggesting to split up the tangent to the power 5 into tangent to the 4 and tangent. And that's an excellent suggestion as well. If we break up the tangent to the 5 as tangent to the 4, and let me bring that extra tangent back here into tangent x secant x, and you recognize this as the derivative of secant. The derivative of secant is secant tan. So if everything else was in terms of secant, then you'd be good to go. Well, this tangent squared plus 1 was actually secant squared to begin with. And this tangent to the 4 can be viewed as tangent squared squared. This tangent squared plus 1 is secant squared. And tangent squared is secant squared minus 1. So tangent squared is secant squared minus 1. You've got that squared, you've got a secant squared, and then you've got a secant tan. So a bunch of secants times secant tan, exactly what you want. So if you let u be secant, then du is secant tan, and we're in business. Right, the secant x tan x dx is your du. U squared minus 1 all squared, u squared, there it is. Now simply expand that, and we're good to go. This u to the 6 minus 2u to the 4 plus u squared, 1 over 7 secant to the 7 minus 2 over 5 secant to the 5, 1 over 3 secant cubed plus c. Office hours are over the Zoom, indeed. Yeah. Over the Zoom link given in the office hours file, right? All right. Now here's the thing. Absolutely, right? I mean, here's what I do in general. I mean, you might not know this, but when the exam is done in the gym, right? Midterm and final exams, when they're in-person exams, for calculus, I announced at the beginning of the semester that we would take all the questions from the exams from the odd numbered exercises in the book. Right, so this is incentive for you to do lots of exercises from the book, and this is how you learn the material. Is it blurry for a lot of people? Do you want to take a moment to refresh this? Well, my camera seems to be fine. I see on my screen. Is there a but? No, there's no but. But I mean, there is a but because final exams are not in-person exams in this semester, so that's not going to happen. Right? I mean, it would be trivial for anyone with a solutions manual to figure out what question we're talking about, look in the solutions manual and copy down the answer. I'll give you a moment to refresh. Try refreshing. Again, Very good. All right, back to this. You have an integral involving tangent, secant, and cosine. Not desirable at all. You know, I mean, you see that secant and tan work very well together. Sine and cosine work very well together. You probably don't want tangent, secants, and cosines. So simplify. Right? You either rewrite everything in terms of 1 over cosine is secant, so this is easily seen to be the same as this. I mean, you could have decided to convert everything to sine and cos, but, you know, since tangent and secant work very well together, and as suggested, you could rewrite this as break up the secant cubed into secant and secant squared. And you see that this is the derivative of secant. And everything else is written in terms of secant. You're done. Simple U substitution. Leaves you with the integral of u squared, or 1/3 secant cubed. So you see what's happening, right? I mean, it's just a question of playing around with the integrand, getting it into a desirable form, and you're good to go. Now remember, earlier I said we should try to stay away from something like a sine 2x multiplied by a cosine x. But sometimes you have no choice. Right? What if that's actually the question? Well, we actually have sum and difference identities for sine and cos. Sum and difference identities that you know very well, or at least that you have seen before. Sine of x plus y, sine x cos y, plus sine y cos x. Similarly, cos of x plus y, cos x cos y, minus sine x sine y. Still the same page, absolutely. Right? Sum and difference identity. Well, I mean, here we have these sum identities for sine and cos. But that's really all you need, because you can use the fact that sine is odd and cosine is even, and say that cos of x minus y, right, by using the same identity, this is cos x, cos of minus y, minus sine x, sine of minus y, but cosine is even, so cosine of minus y is the same as cos y, and sine is odd, so sine of negative y is negative sine y. And now, if you look at this, you have sine of x, sine of y. So if you use these two, right, if you do this minus that, or this minus that, so cosine of x minus y minus cos of x plus y, right? This minus that, these cancel out. This minus that, minus minus, gives you 2. Does everybody see that? So sine of x, sine of y is 1/2 cos of x minus y minus cos of x plus y. A lot of books will give you this as an other identity, but you can work it out using the sum identities as we've done here. So what does this mean for us? Sine of x, sine of y, this is 1/2 cosine of x minus y minus cosine of x plus y. Or, if you prefer, 1/2. This is cosine of minus 4 theta, but cosine is even, so this is cosine of 4 theta minus cosine of 8 theta. Yeah, exactly. That's the beauty, right? All you need are these two. Just these two. You can get the difference identities using the fact that sine and cosine are odd and even respectively. And then you can get these identities by just subtracting. Two minus 6 is -4, but again, cosine is even. So cosine of -4 is the same as cosine of 4. That's the thing. And that's why people dislike math. Because, in high school, you think that it's all about memorizing a bunch of formulas, but it really isn't. It's about putting things together and understanding. And if you understand, there are very few formulas to learn. And you're good to go. Let's finish that up trivially, right? Antiderivative of cosine 4 theta, 1/4 sine 4 theta, minus 1/8 sine 8 theta. Throw in your arbitrary constant, and there you go. Yeah, why don't they try to make it fun in high school? Here's what I think is happening. A lot of people teaching high school math don't know math. I think it's changing now. I think if you're going to teach high school math, you need to do lots of math courses. But I think in the past, some just didn't know. I mean, there are, of course, exceptions. My secondary 3 professor had a PhD as well in mathematics. We did not learn a single thing. It wasn't good. But she was very smart. Number 60 is asking us to prove the reduction formula. All right. Prove the reduction formula. Seems like a lot of work. Seems overwhelming. It really isn't. And the book has a bunch of these reduction formulas. First of all, I don't want you to use them. But it's a nice exercise to prove them. This is not -1, this is n not equal to 1, and being a natural number. Right, so how do you prove these things? I want to say they're all proven in the same way. It's just one simple application of integration by parts. One simple application of integration by parts. Let's do it, Michael. What are we going to take for u and what are we going to take for dv? Exactly right. We're going to break this up as secant to the n minus 2 times secant squared. Absolutely. So sorry, Graham, I know I wrote -1, I meant +1, so that you don't get a 0 in the denominator here. And n should be a natural number, so no negatives. So 2, 3, 4, and so on. N is an element of the natural numbers. Right, so break it up this way, where secant squared, you know the antiderivative of secant squared, right? So dv is going to be secant squared, something you can find the antiderivative of with relative ease. U is going to be secant to the n minus 2. So in that case, the derivative, n minus 2, secant to the n minus 3, times the derivative of the inside. Derivative of secant is secant n. And if dv is secant squared, the antiderivative is tangent. So antiderivative of secant squared, secant to the n, right? Integration by parts, uv secant to the n minus 2 tangent minus the integral of v du. Let me pull out the n minus 2. This times this is secant to the n minus 2. And then you've got a tangent squared. And then you have a tangent squared. But as you know, tangent squared is secant squared minus 1. So if you multiply this again, you recognize that you'll have a secant to the n. Exactly what you started out with. You know where this is going. Let me split it up into two pieces. Secant to the n minus, so minus, that'll be a plus. Secant to the n minus 2. And right, you see what's going to happen? This is the integral you started out with. So if you bring this to the other side, you have n minus 2 plus 1 of them, so you'll get n minus 1. How did we find the du? It's just the derivative of this. This is something to the n minus 2. So you differentiate the power, and then you multiply by the derivative of the inside. Chain rule. JD is asking what exactly is a reduction formula. We're looking for the integral of secant to the power n, blah, 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 integral of secant to the power n minus 2. You are reducing the power of secant. So you see, if you had like secant to the 100, you could use this, and then you'd have the integral of secant to the 98. But you could apply that again, the integral of secant to the 98, blah, 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 secant to the 96. So the powers are going down until you get to 0. Or 1, or something that you can integrate. Shouldn't we have a secant to the n minus 3 in the second line? Well, we have this times that, so I have combined them to get a secant to the n minus 2. This thing right here, I mean, it's n minus 2 times this whole integral, which was itself 2 integrals. Right? Integral of secant to the n minus the integral of secant to the n minus 2. So does everybody see where this is headed? Right? We're going to bring this to the other side, and we get n minus 2 plus 1, so n minus 1 of these integrals is equal to what remains? Secant to the n minus 2 tangent plus n minus 2 times the integral of secant to the n minus 2. Divide by n minus 1 and you're done. How are we doing? This bringing it to the other side business is so nice. It is very, very nice. All right, this whole discussion took longer than I expected. Next time, are you talking about the n minus x in the original formula? There was no n minus x, right? Where did the n minus 1 come from? We had n minus 2 here. When you bring it over to the other side, first of all, the negative becomes positive. So n minus 2 plus 1 gives you the n minus 1. All right. Next time, we're going to tackle integrals like this. I mean, we have a lot of techniques so far. Integration by parts, U substitution, but nothing that allows us to answer how do we find the antiderivative of this. So that's what we're going to do next time. Any chance we can do another proof question for next class? I mean, it is midterm material, absolutely. You could be asked to prove a reduction formula on the midterm. And yeah, exactly, Michael, right? I mean, Michael is suggesting, can we generalize this to an a squared? And absolutely, they're done in exactly the same way. So we'll see that on Thursday. Thank you all for coming, folks. And I will see you then. Practice this in the meantime, right? These trig integrals. Do some more. And you'll see, as Rafiq suggests, it's trig substitution. So it's no coincidence that we did trigonometric integrals before, because now these kinds of questions will all involve trigonometric integrals. Jun Shen is asking, so I mean, I'm happy that you're back. Isn't that a circle? So if this was a definite integral with nice bounds, it would be easy to evaluate. But here, if I'm just asking for the antiderivative, the fact that it's a circle does not really help you here. But we'll tackle this next time. Thank you all for coming, and I will see you on Thursday.